Our first video on fluid dynamics talked all about flow, both fluid flow rates and the continuity equation, specifically looking at if we change the cross-sectional area of a pipe, how that will force the fluid to speed up, slow down, etc. But while we were discussing how fluid is flowing, we really didn't discuss why those changes occur. And that's going to be the subject of today's video, looking at 1, the Bernoulli effect, and 2, the Bernoulli equation. So the continuity equation tells us that when we have a thick pipe like this and it narrows down, that fluid velocity is going to increase. It's going to be moving slowly and then it's going to speed up. But why exactly does this effect occur? Well, keep in mind, back from AP Physics 1, that if we have any sort of acceleration, that tells us we must have a net force. And specifically, the net force here must be going to the right because the acceleration is to the right as this fluid speeds up. Well, let's try to look at this in a little more detail. We're going to do that by zooming in on this particular point in the fluid. And we're going to look at this little dot right here. And for it to have a net force to the right, there must be a bigger force pushing to the right than there is a force pushing to the left. What are the sources of these forces on this little packet of fluid? Well, if we think about it, what's the only thing that could be pushing it either direction is the fluids on either side. And so really what this is telling us is that the fluid on the left is pushing with more force to the right than the fluid on the right is pushing back to the left. And keeping in mind that this is over a certain area, what this actually tells us is that the thicker end of the pipe, the left-hand side here, must have a higher pressure because it's providing a higher force than this section over here on the right does. So higher pressure, lower pressure. And this is a pretty key idea. The idea that fluids accelerate, typically speaking, when there is what is known as a pressure gradient. Now this is going to be a somewhat new term to you, but really all pressure gradient is telling us is that there is a difference in pressure. So essentially we have pressure going from low to high, or high to low, etc. So once again, kind of looking at the situation we were just looking at, we have fluid that is going at a low speed and then it speeds up as the pipe narrows, and that tells us there must be a net force and an acceleration to the right, because for it to speed up, the velocity and the acceleration must be in the same direction. And that therefore tells us that we have higher pressure at the wider end of the pipe when it's moving slower, and lower pressure at the narrow end of the pipe when it's moving faster. And if we look at the flip side, well, we're going to see the exact opposite effect. That if we have fluid going from a narrow pipe to a thick pipe, it goes from a high velocity to a low velocity. But that tells us there must be a net force going against this fluid flow, an acceleration going against it, causing it to slow down. And that in fact tells us that we have a lower pressure, once again in the narrow region, and a higher pressure in the wider region. Now this was formalized by a Swiss mathematician and physicist named Daniel Bernoulli, and therefore we give it the term the Bernoulli effect. That a decrease in the pressure of a moving fluid causes an increase of the velocity of the fluid, and that an increase in the pressure of a moving fluid causes a decrease in the velocity of the fluid. Or if we want to simplify it even more, we can say when we have lower pressure, the fluid is moving faster, and when we have higher pressure, the fluid is moving slower. Now, a couple key things I want to point out here. One, notice I just say this is the Bernoulli effect. That term effect doesn't sound, it's not like a law or something like that, and that's because this is not always the case. We're going to see that on a little bit more in the video, but most of the time, this is a good way for us to think about it. The other point I want to bring up, though, is that this is somewhat counterintuitive. That typically we think if something has high pressure, well, then it's pushing really hard and it must be moving faster. And we're seeing this is actually not what's happening here. So let's kind of zoom in and figure out what exactly is going on. So first off, let's solidify what causes changes in pressure. Now, there are a couple different ways we've now described this, and the first one was one that we talked about with fluid statics, which is if we want to increase the pressure on a fluid, we need to go to a greater depth, so lower down. So if I have a pipe going from some higher point to some lower point, well, we're going to have greater pressure at, for instance, this lower point, because more fluid is literally pushing down on it from above. Similarly, if we have it going from a lower point to a higher point, even if the fluid is flowing to the right, we're still going to have more pressure here because this fluid on top is pushing down on the fluid down below. Now, the other one we just saw, and this sounds a little bizarre, but also changes in cross-sectional area also affect the pressure as well. When we look at it, we see that we have higher pressure when we have a wider pipe and lower pressure when we have a narrower pipe. So why exactly is pressure directly proportional to cross-sectional area? So to make sure we understand these diagrams here, what we're saying is when the area is wider, we actually have a higher pressure. And when the area is lower, we have a lower pressure. And as a quick reminder, we already saw this with the continuity equation. Then when we have that wider pipe, it's going slower. When we have that narrower pipe, it's going faster. So this top situation, it goes from fast to slow. The bottom situation, it goes from slow to fast. So let's think about it like so. Let's say you have a hose, for instance, and initially it has this area in the hose, this area at the opening, so A1 equals A2. And then when we stick our thumb over the end of the hose, we've significantly shrunk this area in the pipe, and so in other words, A1 is much bigger than A2. Now, let's think about this bottom situation first. Now, when we do this, when we put our thumb over the end of the hose, what we're doing is we're applying a force back to the fluid inside the hose. But because of Newton's third law, that means that this fluid is applying a force back. But we also know from pressure that if we have a force on this fluid, well then that force has to be going in all directions. So therefore we actually have a force going up, down, to right, all over from this one particular packet of fluid. Meaning that we actually have a much higher pressure inside the hose than outside the hose, because we have much more force being applied from the fluid inside the hose than outside the hose. In fact, if we look at this initial situation, outside the hose the pressure is atmospheric pressure, and there are no changes in the area of the pipe here, so all the way back here it is also atmospheric pressure. If we look at the second situation, we have atmospheric pressure on the outside. It has to be that way because we are in the atmosphere. But inside, the pressure is significantly higher as a result of the force being applied. Additionally, we know because of the fact that the pressures here are equal and that the areas are equal, the fluid is going to flow all at the same rate. When we did it down here, what happened is we have a higher pressure, a bigger area, a slower moving fluid, and then when we put our thumb over it, the water that comes out has a smaller area of pipe, a much lower pressure, and actually moves faster. And the reason why the fluid is speeding up is because we have greater pressure behind it, pushing it forward. Now, if we look back at the pipe situation, it's really kind of the same idea, that if we have fluid going this way into the narrower section of the pipe, what's happening is that this fluid is literally being squeezed with forces back on it. And when it's being squeezed that way, those forces are redistributed, push all directions. That creates a higher pressure in this region, and then a smaller pressure later on because it's no longer being squeezed. The squeeze has already happened. Now, I started to talk about this just a second ago, but now is really the crux of this whole idea, which is why is the pressure inversely related to fluid velocity? And there's a couple of different ways we can think about this. The first is a way we've already been concentrating on, which is that high pressure correlates to high force and low pressure correlates to low force. So let's concentrate specifically looking at this area over here. If we look at these two pipes, and specifically if we zoomed in, we would see that there is a higher pressure in the thicker part of the tube, so lower pressure in the thinner part of the tubes, and therefore we're going to have a net force from the thicker part to the thinner part. So this first one, we have a net force going back towards the thin part, but since the fluid is moving to the right, it is therefore going to slow down. Whereas in this bottom situation, we have a higher force in the initial thicker part. It's going to the right. The net force is going to the right to the smaller force area that's going to cause the fluid to speed up. But now let's look over at the pipes on the left. In this one here, we have at a smaller depth going to a much bigger depth. And additionally, we have one going from a bigger depth to a smaller depth. And we talked about the fact that we know that there must be more pressure here at the lower depth and less pressure at the higher depth. And so we might be thinking, okay, that means if that is the case, lower pressure is related to fluid velocity, so therefore it should be going faster here, and then it's going to slow down, and it's going to go slower, and then it's going to go faster here. But there's a problem. The pipes have the same diameter throughout. They're not thickening or thinning. So therefore, according to the continuity equation, the fluid velocity should be the same throughout these pipes. Well, how is that possible? We're actually going to look at this in a slightly different way that might help you conceptualize it a bit better. Rather than concentrating on forces, which does help us part of the time, we're going to move beyond that and instead focus on thinking about energies. And specifically, thinking about the fact that high pressure corresponds to what we call a high energy density, and low pressure corresponds to what we think of as a low energy density. So let's pause for a second and even kind of break this down a little bit more. If I have pressure, the equation for pressure is force over area. Now, what I'm going to do now is a small little derivation. I'm going to start off by saying I'm going to multiply this by 1. Still gets force over area. But if it's 1 is the same thing as saying I'm going to multiply something by some number over itself. So specifically, I'm going to say delta x over delta x. And when we do this, what's a force times a displacement? Well, really, that's work. And what is an area times a displacement? So I have an area and I'm moving it forward. Well, that's going to be over volume. So what this is really telling me is that pressure is essentially the energy density of, specifically, work. And what does that mean? A better way to think about it is, if I have a fluid, it could have the capacity to do some work. And we're going to say when a fluid has a high pressure, it has more energy available to do work. And when we have low pressure, it has less energy available to do work. So, for instance, looking at these situations, whenever I have high pressure, so on the left-hand side, when it's at a bigger depth, a lower height, we have more energy available to do work. And if we look at the side on the right, when it is at the thicker pipe, it has higher pressure, therefore more energy available to do work. Well, how exactly is this energy expressed later on? Well, when I have it going from these thicker pipe to narrower pipe, for instance, where does this energy go in that higher pressure? It goes toward, when the pressure decreases, the fluid speeding up. It goes to the kinetic energy of the fluid. Similarly, if I have a fluid that slows down, that kinetic energy is being converted to this pressure, this ability of the fluid to do more work later on down the pipe. Similarly, if I look over here, I have high energy density, a lot of energy available to do work at this higher pressure, and what is causing that is not for the fluid to speed up. The fluid goes at the same rate, but instead the fluid is having to gain gravitational potential energy. So that work lifts the fluid and becomes gravitational potential energy. And similarly, if it has a lot of gravitational potential energy and it flows down, that is now available to later on do work later in the pipe. So now we've had a lot of things happening. We've had fluids moving up and down, their velocities are changing, the pipe is getting narrower and wider, the pressure's changing. There's so many factors here that now it's a good idea to start trying to contain it all into a single equation that will allow us to analyze any of these situations. So I'm going to do a derivation right now, and I'm never going to ask you to do it again, but I really want you to go through this with me because you can see where all of the details come from. So let's say we have a fluid moving through this pipe that not only moves upward, but also is getting narrower. So we have two different effects happening at the same time. Well, we automatically know that the cross-sectional area of the thick pipe is significantly bigger than the cross-sectional area of the narrow pipe. That's pretty easy. But additionally, we know from the continuity equation that automatically, remember, a thick pipe means slower fluid velocity, and a narrow pipe means faster fluid velocity. So it's going slower in this area 1, and it's going faster in this area 2. But additionally, we now know from the Bernoulli effect a couple of different ways that the pressure must be significantly higher down here in the first region than later on. And there are two reasons for that. One, the pressure is higher here because it's at a lower depth, so more fluid is pushing back on it compared to this area up here. But additionally, we have a thicker pipe, so significantly higher pressure at this area 1 versus area 2. All right, so now let's start doing something we haven't done in a while, which let's actually draw some energy bar charts. So we'll go and keep in mind, we're going to say y equals 0 is this line down here. So they're both above that point. And if we look, well, we have at this first region, it's moving slower. So it has less kinetic energy than at the second region. But it's also lower, which means it has a lower gravitational potential energy than at the second region. Well, evidently, these bars are no way, if we add them together, they're not going to get the same total. So energy is actually not conserved here, at least not yet. So we need to think about this as, okay, this fluid, in order to speed up, the fluid back here must be performing work, pushing it forward. Now this region up here, you might be wondering, well, why is this work negative? And you have to keep in mind what's happening is this fluid later on is actually pushing backward, but it's not doing it nearly as much because it's moving out of the way. So it's pushing back a little bit, but not a whole lot. Let's go ahead and actually start saying a couple different things. One, the same volume of fluid must pass any point in the pipe. So we're going to say that this volume of fluid right here, V, well, actually really kind of think of this as V1, is the same as this volume of fluid, V2. And we can see that because this one's so much narrower than this one, what's really happening is at the same amount of time, this one's moving slower than this one is. This one is covered a smaller distance in the same amount of time than that one because it's flowing faster in the second region. Now let's start to have this derivation, which is if we look at this chunk right here in the middle, the net work on that chunk is going to be the work from 1 and the work from 2. And if we look, so we have work as force times distance. So this net force is being applied over this distance, delta x1, and this net force F2 is being applied over this distance, delta x2. But we should change this. This really should be a minus sign, because whereas this fluid in section 1 over here on the left is pushing it forward, this fluid in section 2 is actually pushing it backward. So we have this going on here. Now, we're going to do something a little tricky, which is I'm going to multiply both of these by 1, and specifically how I'm going to do that is I'm going to say I multiply this first region by A1 divided by A1, so A1 over A1 is just 1, and I multiply the section 1 by A2 over A2. Well, what's the reason for doing that? Well, 1, a force over an area, that is just a pressure, and a delta x times an area, well, that's really just a volume. So what I've done is I've actually made this a little cleaner and said, okay, I have P1, the pressure at 1, times the volume, minus the pressure at 2 times the volume, keeping in mind that these volumes are actually the same size. So let's say we're comparing one point at the wider pipe and one point at the narrower pipe. So looking at these 2 points, and if we want to look at the change in energy between these 2 points, as we saw in the energy bar charts, well, there's a change in kinetic energy plus a change in gravitational potential energy. And because that energy is actually not conserved, there is a change in energy. Really, that change in energy is the net work. Now let's go ahead and expand these equations out, which is the net work we just saw in the previous set of slides was P1V minus P2V. So the pressure at point 1, the pressure at point 2, and the volume. And if we look at the kinetic energy, the change in kinetic energy, well, kinetic energy equation is 1/2 mv squared. The mass is not going to change, it's just the velocity change. So we have 1/2 mv2 squared minus 1/2 mv1 squared. Additionally, if we look at the change in gravitational potential energy, we're just looking at the changes in heights, specifically mgy2 minus mgy1. But this is a fluid, we don't typically deal with mass, so remind ourselves that density is mass over volume, and we can say therefore that mass is equal to density over volume. At this point, that point, and that point, I'm going to substitute in, for m, the mass, the density times the volume. Okay, now looking at this, there's something that we may notice, which is that we have volume in every single term. So I'm going to divide every piece here by, note, capital V, not lowercase v, which is velocity. We're going to divide everything by capital V. And we are now left with this. P1 minus P2 equals this chunk over on the right. Now, this is actually pretty much done, But the issue is I want to be able to compare 2 points in the flow, and so I'm going to put everything that talks about one point on one side of the equation and everything that talks about the other point on the other side of the equation. So I'm going to move everything with a 1 over to the left-hand side, and I'm going to move this piece of a 2 over to the right-hand side. So I'm basically just adding all of these across. And we are left with this final equation right here. So that leaves us with this seemingly long and kind of convoluted equation called the Bernoulli equation, which was not discovered by Daniel Bernoulli, but named for him because of his work for the Bernoulli effect, which is P1 plus 1/2 rho V1 squared plus rho GY1 equals P2 plus 1/2 rho V2 squared plus rho GY2. Okay. There's a lot of pieces here, so let's talk about the details. Now, first off, I'm actually going to jump down here real fast. This is talking about 2 different points in the same laminar flow of fluid. So everything on the left-hand side corresponds to 1 point in this flow, and everything on the right-hand side corresponds to a point somewhere else in the flow. And this is allowing us to look between these 2 points and say, okay, there's changes in heights and velocities, well then there are these changes in pressures, etc. And keep in mind this is only for ideal fluids, so liquids, basically incompressible, only laminar flow, etc. And if we look at all of the pieces, well, P1 and P2 are the absolute pressures. Keeping in mind absolute pressure means you have to include atmospheric pressure. If you want to know the gauge pressure, then you would take that pressure and you'd subtract out atmospheric pressure from them. Okay, we also have G in 2 different points. G is the acceleration due to gravity, which is approximately 10 meters per second squared here on Earth. The density of the fluid, which pops up a lot, is in units of kilograms per meters cubed. It's going to be the same density because we're looking at the same fluid flow. The fluid velocity, V1 and V2, is in just meters per second. And this is a real one we have to be careful with. Y1 and Y2 are the height of the fluid above Y equals 0. And this is really annoying because previously we learned that H is actually the depth of the fluid when we're looking at, for instance, the absolute pressure and gauge pressure equations. That's the depth. Y is in fact the height, how high it is above whatever we set as Y equals 0. But recall, another way we can think about pressure in the situations is as an energy density, specifically of work. And in fact, we can think of every piece of this equation as an energy density. And when I say energy density, all that means is it is energy divided by volume. So you can kind of think of it as the energy present in a piece of fluid doing various things. So the pressures, once again, P1 and P2, are really just the energy available to do work, to do other things. If you have a higher pressure, you can speed it along or raise it up, etc. The 1/2 rho V1 squared, well, that looks a lot like 1/2 mv squared, and these are in fact, we can think of it as the kinetic energy density, how much energy is being devoted to moving the fluid around. And rho Gy1 and rho Gy2 are the gravitational potential energy density, the amount of energy that's been gained by the fluid by being raised up. So really, this equation is actually just a reformulation of the conservation of energy. And in fact, if we now look at the continuity equation and the Bernoulli equation, well, they're both pretty much reformulations of extremely important laws. The continuity equation is conservation of mass, that the fluid can't just disappear through the pipe, and the Bernoulli equation is conservation of energy, that this energy must be going to other situations. That energy can't just disappear as the fluid moves on. Neither one really trumps the other. They both work continually in tandem. So to wrap up this video, let's look at a practice problem. And I'm going to go ahead and warn you that whenever we do problems involving the Bernoulli equation, there are a lot of moving parts. A lot of numbers are going to be thrown at you. It's not particularly hard. All the math is actually fairly basic, but it's extremely easy to forget what number goes where and to get some stuff mixed up. So let's say we've got this particular situation. So we have this pipe that's wider and then narrows down and also drops in depth. And we want to know what is the gauge pressure at the bottom here. So go ahead, if you think you can do it, pause it, give it a try, give it your best shot, come back, and let's see how you did. So remember, neither the continuity equation or the Bernoulli equation trump either one. They're both going to apply. And looking here, probably the first thing we need to think about doing is, okay, let's talk about the continuity equation first, which is that the volume flow rate in the top must equal the volume flow rate at the bottom, because this is one laminar flow, and the continuity equation tells us that A1V1 equals A2V2. V2. Now we could solve for these areas, keeping in mind we'd have to convert them to meters, and the area of a circle is pi r squared. We could do that with this velocity and end up doing all the math and getting that the velocity at the end is 8 meters per second, which makes sense, should be going faster because it's a narrower pipe. Another way to think about it is that the radius at point 2 is half the radius at point 1. Now, if we have that radius is going to be squared in the area equation, that means the area at point 2 is going to be 1/4 as much as it is at point 1. And if it's at 1/4, those have to balance out the velocities. The velocity at point 2 is going to be 4 times as much as it was in point 1. So we have 8 meters per second compared to the original 2 meters per second. And now that I have this velocity at point 2 is 8 meters per second, we can now utilize the Bernoulli equation. So keep in mind, we're trying to find the pressure at point 2. So I've written out the Bernoulli equation here, and the first thing I'm going to do is I'm just going to basically move everything to one side except for what I want, which is the pressure at point 2. So I have all of the points at point 1, but then I subtracted across all the parts that involve 2's, and additionally, I went ahead and just simplified this a little bit by pulling out the 1/2 in the row from these two pieces. I pulled out the rho and the g from these two pieces, so I get this equation here. And I'm going to go ahead and just stick in all of the numbers. Now, the thing we need to be careful of, though, most of these are pretty straightforward. The density, it's water, that's easy. The velocities, easy. Density, the heights, difference in height, easy. The only thing that might trip you up is if I look at P1, remember, that's an absolute pressure, and I gave you a gauge pressure. So we need to add 200 kilopascals, or 2 times 10 to the 5th pascals, plus atmospheric pressure, which is 1 times 10 to the 5th pascals, in for P1. When you get to this point, you're going to need to pull your calculator out. Be very careful with your signs. We stick all the numbers in, and we get an absolute pressure of P2 is equal to 285,000 pascals. But the issue is that we didn't ask for the absolute pressure at gauge 2, we asked for the gauge pressure. And keeping in mind that the absolute pressure is equal to the gauge pressure plus atmospheric pressure, we need to subtract atmospheric pressure out, and we get a final answer, a final gauge pressure of 185,000 pascals. So in this particular situation, the gauge pressure actually went down. And that might surprise you because it's lower, but it's also moving faster. So apparently the fact that it's moving faster overcame the fact that it is lower down. So what are the main takeaways for this video on the Bernoulli effect in the equation? Well, one, can we explain what causes fluids to accelerate, which is simply a pressure gradient, aka differences in pressure. Can we utilize the Bernoulli effect to conceptually predict how the pressure and thus the velocity of a fluid changes? Now remember, this is a little more complicated than it initially seems. Typically speaking, if you have higher pressure, the fluid is going to be moving slower. If you have lower pressure, the fluid is going to be moving faster. Wider cross-sectional area, high pressure, lower velocity. Narrower cross-sectional area, low pressure, higher velocity. However, this can be complicated if we start moving things upward and downward, because then we have to start thinking about the pressure differences from these depths. And that's when we need to also be utilizing the Bernoulli equation to calculate the various factors in some flowing fluid. So whether it's its absolute pressure at multiple points, what is it, how fast is it flowing, how high it is, etc. That equation alone encompasses almost everything we've done here today.